Chapter 15. Matrix Methods. This chapter covers ciphers using multiplication by a matrix of integers or a matrix of ring elements, ciphers using multiplication by large and small integers, solving linear congruences, constructing rings and invertible matrices. Matrices are a tool well suited for cryptography because they can encipher arbitrarily large blocks of text in one operation. Typically, each block in the message is treated as a vector of bytes, meaning integers modulo 256. When Sandra uses a matrix to encipher a message, Riva must use the inverse of that matrix to decipher the message. Let's begin the discussion of matrix methods with a technique for inverting a matrix. Section 15.1. Inverting a matrix. There are several ways of solving a matrix equation such as C equals AP when there is known plaintext. Since Emily knows P and C, but does not know A, she can solve the equation for A by right multiplying it by P prime to get CP prime equals APP prime equals A. So Emily needs to invert P. Riva does the opposite. She knows A, but does not know P, so she needs to invert A. Left multiplying the equation by A prime, she gets A prime C equals A prime AP equals P. The method illustrated here has the advantage of obtaining the inverse matrix directly without the intermediate step of back substitution, which is required for other methods. The method is to place the given matrix side by side with the identity matrix in an n by 2n double-wide matrix. The left size is reduced to an identity matrix using only elementary row operations. These row operations are applied across each row of the double matrix, so as the left half changes from the original matrix to an identity matrix, the right half changes from an identity matrix to the inverse of the original. The elementary row operations are 1. Multiplying a row by an invertible constant, 2. Swapping two rows, and 3. Subtracting a multiple of one row from another row. The algorithm turns the elements of the original matrix into the elements of the identity matrix one by one, starting in the upper left corner, then working down the left column. Then it does the same for the second column, and so forth. If at any time the algorithm gets stuck, meaning that all of the elements in the active column are multiples of 2, or all of them are multiples of 13, then the matrix is not invertible. If this happens to Sandra, she needs to try a different matrix A. It is often sufficient to add 1 to some element on the bottom row. If this happens to Emily, she will need n more characters of known plaintext. This will give her a brackets n plus 1 times n matrix. When she applies this algorithm, the inverse matrix is in the upper right n times n portion of the double-wide matrix. Here is a 3 by 3 example. This matrix works on the 26-letter English alphabet, so the matrix elements are integers modulo 26. There are no fractions and no negative numbers involved. Since this is done modulo 26, each element that is not a multiple of 2 and not a multiple of 13 has a multiplicative inverse. This lets us turn the first non-zero element in each row into a 1, which makes it easy to decide which multiple of a row to subtract from any other row. The original matrix is. This gets expanded to double-wide format by appending a 3 by 3 identity matrix on the right. You are immediately in trouble because none of the first elements in any row is invertible. I did this deliberately in order to show a very useful trick. The first element in row 1 is a multiple of 13, but not a multiple of 2. The first element in row 2 is a multiple of 2, but not a multiple of 13. If you simply add row 2 to row 1, then the first element becomes 19, which is a multiple of neither 2 nor 13, hence it is invertible. Problem solved. The multiplicative inverse of 19 is 11 modulo 26, because 9 times 11 equals 209, which is congruent to 1 mod 26. You multiply row 1 by 11 to turn the first element in the matrix into a 1. Now you can finish column 1 by subtracting 6 times the top row from row 2 and subtracting 10 times the top row from row 3. This will set the first element in rows 2 and 3 to 0. Time to work on the second row. The first non-zero element on row 2 is 9. The multiplicative inverse of 9 is 3, because 9 times 3 equals 27, which is congruent to 1 mod 26. You multiply row 2 by 3 to turn the first element in the row to a 1. This lets you finish column 2 by subtracting row 2 from row 1 and subtracting 25 times row 2 from row 3. Notice how the left side of the double-wide matrix is gradually turning into the identity matrix. Almost done. The first non-zero on row 3 is 21. The multiplicative inverse of 21 is 5, so you multiply the bottom row of the matrix by 5. Now you can finish the third column by subtracting 9 times row 3 from row 1 and subtracting 19 times row 3 from row 2. Done. The left half of the double-wide matrix now holds the identity matrix, and the right half is the inverse of the original matrix. You can check this by multiplying the original matrix by the inverse. The result should be the identity matrix, and it is.